Okay. We should buy chocolate for them.
Yes.
And you should buy chocolate. Not me. So, now we are going to talk about what we discussed. So, just by simulation, to start, modelize the grids, load, and connect converter, and just provide the open loop. And if you have enough time, we can go with the proof. Okay? So, by this, you need to get the. Do you have a white? So, now start lighting grid, three-phase grid with 400 volts. So the frequency is 50 hertz, and voltage is 400 volts. So then the grid has the impedance, and each phase has the impedance of, I don't know, 0.01 plus J 0.01. Then provide the measurement here to see that your voltage and your current So you need to go to open the MATLAB, to escape, grab the three-phase voltage, this three-phase voltage, three single phase. I need a three-phase. Okay, so you open this and just open. Yes, three-phase source. Just look for the three-phase source. Yes. This is three-phase, we are looking one three-phase, okay, not three single-phase. You can actually search for voltage source, something like this, then you can easily. Yeah, this is nice. Yeah. But just connect it and then you can do the value. Three phase, not three single phase. One three phase, not three single phase. They have the same meaning, okay? But I'm going to sorry. you can also so you can go to Simscape and then discover additional something, and in the sources you can easily find it. And measurements, their name. Okay, sorry. I didn't tell you. Yeah. I didn't say you. So, yes, you have already internal in three-phase system. You have source and resistance, so you don't need to create another line for the resistance. Because you have actually, the source have already. Yeah.
Power supply
Exactly the same. Yeah, basically. Yeah. No, you're not going to use the converter. So it is the DC circuit, it is the AC circuit. No, this is like do you have to no, this is okay, for the load you can consider just a linear RL load, okay? So you go to the element, choose the RL or active reactive load, so you can consider something like this. So did you finish this part?
Yes.
Yes, what is the value of the current? What is the value of the current and voltage? You said yes. Show me the current and voltage by oscilloscope. I'm going to check. Current and voltage. Oscilloscope measurement. Oscilloscope measurement. Measurement. Voltage and current measurement. Voltage and current measurement. Voltage and current measurement. Face to face, 400. Face to face, 400. This is face. So you can divide it by square root of 2. But that was RMS space. This is RMS. Look at here. Why say that face to face? This is phase A, and this is phase B, and this is phase C. Okay? Face to face means this one means line. Okay? And RMS value. It said that RMS value is, I don't know, something, but BRMS is equal to V max over square root of 2. So if it said that RMS value we need 400 volt. Maximum is 400, okay, not RMS. So you should tune your RMS value in a way to have 400 volt maximum. Okay? If you are going to write this voltage, but once you go to simulation, you need to go to one 10 seconds. But 1 second is what means the current of voltage. You remove that loss, then it goes. Because you are using for the continuous ones. Yes. 400 you remove that loss, then it doesn't cover any. Look, we use a switch. Switch is working but what we choose is the knowledge. So, tell me. Yeah, but you didn't find the right value. No, base should be 400 times 2 square root of 2. Yes. Times 2. Yes. Yeah, but this is 200. We are looking for 400. So times 2, 400 times 2 square root of 2. But you times 200 times 2 square root of 2. Why you are not actually providing this information? You want to find it? So show me that. Okay, you can hear?
You can see the screen.
Okay, so if you are going to find the power electronic components or power system components, you go to scale. Yeah, okay. And then we have power system here and a specialized technology. We have renewable pack, everything you want. And we have also scale components. So you can find the switches, sources, sensors, semiconductor, passive devices, anything you want, components or connections. So we get this type of things, but the simulation is not based on this. So we go for power system. But if you could not find, doesn't matter. You easily just search and say, okay, I need this one and it goes direction. Because MATLAB is times to times updating. Okay. So open it. So, if you did simulation of linear well, so you can put the one linear load, which, for example, 8 kilowatt and 6 kilovolt ampere rack. Okay, so you go to the components and the end of the measurement goes to the load. So come here to electrical. So just look at here, we go to start by scale, and then we go to the spatialized power system, and after this we go to source, and we choose easily three-phase voltage source. Okay. So if you double click on it, you see the frequency is 60, so you can change it to 20. And then phase-to-phase voltage is 25 kilo, so it is RMS, but we need 400 times to the square root of 2 is 562. Then we mention 0.1 for the resistance, and also we consider, because this is the inductance, but we mention something else, J omega, okay? But you put this one because it is not important. You put 0.1, and that's all we can also work. I mean, it's a L. So L times to J omega. R is 0.1. 0.01. Okay. I mean, the thing that I'm going to show is something else. Okay. So now this is our grid model, and after that we said that we need to measure the. So for running your simulation, you should use the power GUI or graphical user interface. So basically, you can easily Now find the measurement. I don't know where is the measurement, so but from here probably we can sensor and measurements. So we have two options. Just use the three-phase or single-phase. So this is three-phase measurement. So you just connect your components, the terminal of the grid. So now we have an open loop. Okay. Alright. So now you don't need to have 10 seconds. So 1 second and run. So look at here. We have three-phase voltage 400. And I think it's better that even we go for the 0.2 seconds. Cruise here and run it. So this is not pure sinusoidal. Why? Because the sample time is so it shows two phase. Okay, so one phase is 400, phase two phase is 800. If you are going to actually they just split the amplitude of 400, which we are looking for it, then now it is 400. Is it clear for you? No? How many of you guys could reach up to here? None of you? Okay, good. Now we are looking for to connect a three-phase active and reactive load to it. So what we are looking for it is load. Again, go to the simscape and also go to elements. So after that, you should go to the passive, okay? So in a specialized power system, you go to the passive, and you see that they have two similar, actually several similar components, and you should be careful. One of them is series RLC branch, another is RLC load. So what we are looking for is three-phase RLC load. So three-phase RLC, series RLC load. So what we need is this. Three-phase RLC load. So don't make mistake. And then click on it. What you do is 50 hertz and active power is we said 8 kilo, so you put 8, and reactive power inductive is 6,000, capacity is in. So for capacitor, you should put INF. Okay? So now we have phase A, phase B, and phase C. So it means that our grid is supplying a load which is requesting active and reactive power. anybody can explain to me what is happening here? So, for example, we are going to consider this record. Okay. So if you get here, so what do you understand? This is the small one is the current, and this is the voltage. So what is the meaning of this? So let me get back again and make this one 0. So make the reactive power equal to 0. Okay? Then now run it and see the current and voltage are in place. Okay, so you see that I start from the anything and the current is, let me increase the value of the current. So, if we start from 0, the phase is not the same. Okay, so if you increase the value of the active and reactive power, you can see that we have some reactive power from load center which requested from the grid. In fact, it provides the disturbance for the power factor of the grid. But this is not the only reason, because when we consider the grid, also some other inductive impacts can also provided by from the, for example, from the line and transformer we are using. So up to here we had the load connected to the grid, and now grid is somehow support the load. Now we are going to connect the converter to this grid, for example here. So we call it point of coupling. We have 3 phase, and we are going to connect converter from here. So for this case, you need the component again, get back to the scale, and also go to the power electronics here. A specialized power system and power electronics here. So what you need is to choose universal bridge. So universal bridge here. bridge. So by double click on universal bridge, you can say that, okay, I'm going to use myRestore, diode, GTO, MOSFET, IGBT, anything you want. So I said that I'm going to use IGBT for the converter, and that's all. Okay? So now you have the DC side of the converter from here, and AC side, which should be connected to the grid. Okay? Is it clear? And for the DC side, you can easily put the DC voltage source here. Sources. And you have you can choose the DC source here and just put it here. So what is the value? I don't know, 800 for example. So it is like your DG source, and the other part should be connected to the interface system. So phase A connected to phase A, phase B connected to phase B, phase C connected to phase C. But the problem of this is that we didn't consider the RL. So you need to have the RL load, RL not the branch here. So I'm checking with you, please put RL after converter and connect to the interface. I'm coming to see. So I'm coming to check, and I'm very angry if you didn't find the universal bridge. RL is the filter, not for the. So if we connect this converter to the grid, it has the filter here, RL we discussed in the class. It's not this one, okay? So you need to have the RL here. RL branch, not RL load. It's a filter. Got it? If you say no, I'll take you. Okay? Simulation is finished. What is it? Remove that. Because then you don't have switching. Then it gives the error code. So it doesn't remove that one and put the linear load. Yes. Excellent. value is 200 and 100 and value just to show the chart. Yes. Yeah, like this. But for this, I mean, you can choose this one, and yeah, it's correct. The value, I don't know, because then later you should calculate it. Okay? But if you run it now, probably run it. What is it? It's control? No. So, when you connect the converter to the grid with 800 DC volt ton, you see that nothing happening. The reason is that the converter is not controlled. Okay? So now we need to control the converter. So first things we need is that we use dynamic model and transfer it to DQ. So for the dynamic model calculation, we need the Park transformation. And for Park transformation, we need the theta. Theta is calculated by tangent inverse V beta to V alpha. So now you should measure the voltage in the point of common coupling and use the Clark transformation. In your computer, you mentioned Clark, it brings this one. So give the three-phase system and see that V alpha and V beta. Then use the mathematical model of the actually this and calculate the theta. So I'm going to see theta in 5 minutes. If not, you must buy chocolate for next. I'm sorry. 5 minutes. Alpha beta, just mention clock, then you have actually the clock ABC to alpha beta, and you easily get the alpha beta. Done? Now go to the separate, you should use the Emacs, and just you have the alpha beta, then you use the mathematical beta and separate the alpha from beta, then you can go. So, did you obtain the value of the beta? To whom? Split in there. Okay. So, okay. But they have to have 90 degrees shift. So the upper and alpha, and then they become yeah.
Mima, okay.
So look at here. So you have the measure of point, the voltage of the point of contact, okay, VABC. Then you can write Clark. Then you have this block, VABC, which is coming from measurement, and it gives one signal, which is the alpha and the beta. Okay? So then you use the D max. D max. So give this signal to D max, and you have two outputs, the alpha, the beta. Okay? Then when you have the alpha and the beta, you should go to mass operation. We have actually multiplier here and divider here. So you give V beta, V alpha after this. Then what is happening? We have here V beta to V alpha. And then we use again A tangent. This is the theta. It should be like this. Okay? And if you want more, it means that I should make simulation for you. Okay? I will check. Hurry up. Done. I'm getting ready.
Get that.
Make me happy for you with simulation. Alphabet. Go for alphabet. Okay, this one. All right. Go for alpha beta. Alpha beta. What is that one? Do you have a food sound? What is that? What is the input? What is the input? Because the chart of that is so again get back to the color fruit of that toolbox. Yes, yes. So, don't forget that part. Calculate the alphabet, then point out the point. Okay? So use the clock. Library, open the library. And write clock. Okay? Then also and look at the next stage from there. So, okay, one important point. I said that your angle should be from 0 to 300 and return back. It should be like this, okay, like this. Look at here. Angle should be like this. Okay? So, sometimes some mistake happening and angle is like this. And the reason is that instead of V alpha, you put V beta. So you should change the V alpha to V beta. The input should change and then it corresponds. In divider, you should put first V beta, then V alpha. But now you have the V alpha, then V beta. So you made a mistake. You should reverse it. So now you have the theta, and what is the next stage is that we need BD and BQ. So if we consider the direction of BD in reference voltage, it means that BQ should be 0. And it happens when we use the tangent inverse, we need beta to be alpha. So now, if you are going to make sure that your converter, your controller is simulation is correct up to now, you should change your alpha beta to DQ, and if Q is equal to 0, it means that your simulation is correct up to here. So now you have theta, you have VABC, now you search for the Park. Instead of Clark, you should use the Park transformation. In library, you check, now you search for the Park. Why? Because we are going to change it from ABC to AQ. I think, okay, I got it. most of you actually make the mistake for calculation of the theta. So basically, as we discussed, the direction of the VB is in reference if we go to tangent inverse V beta to V alpha. Okay? So if we make the right simulation, in fact VD is a constant value, VQ is equal to 0. Now 50% of you, probably more than 50, have this value. It means that up to here your simulation is correct. Okay? That's all. Now you can go to have lunch. I didn't know because my lunch time was not right now, so I didn't feel hungry. But I forgot. Sorry, apologize.
Fine. And lunch is.
We can have lunch at Simral complex. Okay. At the place. After that, if anybody interested to do the simulation, you come here and do the practice on their own. Okay.
You can save your files if you want to continue with the same system. Okay.